Welcome to the afternoon session of the fourth day of the school. And today we have Andrew Johnson with us. He came all the way from Australia to Finland, and after 1 year there, he came here. I'm kidding. Andrew is... he has a background in biostatistics, in psychology, in medical sciences, and has been using or developing methods for Bayesian analysis in that, say, application areas, but also he's been developing core methods. And he's a Stan developer. Stan is the language that we're going to learn today, which is a very strong and powerful probabilistic programming language. And he's been also working with safe and reliable inference. I guess that's it. With a couple of models, which I just learned now. He works with Aki Vekteri, a postdoc there. Some might have read his books, or his book, the Bayesian analysis book, which is together with other authors, but I guess it's one of the ways that people know Aki's name. Okay, welcome and enjoy.
All right, I think that's on. Cool. Alrighty, well, hello everyone. Welcome to our afternoon session. So today we're going to be talking about this idea of Bayesian workflow and how we can approach Bayesian modeling in a bit more of a systematic and a rigorous way. So just as a bit of background, so a shorter version of this talk was given last year by Elizaveta Semenova, and it was very, very well received, and she was asked to come back and give a longer session, this workshop length, but unfortunately there were visa issues and she couldn't attend, so I was a last-minute replacement to come in. So if you have more questions, I also highly recommend checking out her talk. The slides and recordings from last year, and some of her work as well is really great in this area. So to add to a bit of background about me, as Alizia said, I am a postdoc at Aalto with Aki, and Aki Vetteri's group mainly focuses in this idea of safe Bayesian model building, because we have a lot of decisions to make when we start putting together these models and the processes we make in choosing, building, and comparing them. And Aki's group is all about developing evidence-based recommended guidelines for people to follow to reduce some of this uncertainty. All right, so if we have a quick look at the topics that we'll be covering. So I'll open up with a bit more of a discussion about Bayesian inference in general. Now, I know that it's day 4 of a probabilistic course, so you're probably seeing Bayes' theorem when you close your eyes at night. So I'm going to try motivating it from a bit of a different perspective, looking more at this applied sort of understanding of what it means to think like a Bayesian and what it means in our own terms of thinking. From there, I'm going to talk a bit about why we might need a Bayesian workflow, sort of the goals, the benefits, and really the principles that we have when we want to put this rigorous workflow into action. To help add a little bit of understanding around some of the checks and steps in this workflow, I'm also going to give a very brief introduction to MC sampling. So far, you guys have done a lot of background in variational inference and optimization, and not too much in MCMC just yet. And there are some key components of this estimation process that we want to be checking as part of our workflow to make sure that everything has gone as planned. Now, because in our workflow today we're going to be using the Stan programming language, I'm also going to give a very, very brief introduction to Hamiltonian Monte Carlo, noting that you've already seen a bit about it so far, and also the adaptation to Hamiltonian Monte Carlo called NUTS, or the no U-turn sampler, which Stan really has popularized in the past few years. Now, once we've covered all of that background and sort of those foundations, we're going to be going through a very sort of step-by-step example of how you would apply a Bayesian workflow in practice. Because there are lots of theories and lots of ideas of what are these steps, how do I apply them, what do I do? So we thought the best thing to do was to show in an example analysis what would you do and what process could you follow to answer these questions. And it's those steps that we'll be covering in the Colab notebook that was also linked in Slack. All right, so let's dive into Bayesian inference. So what are the key, I suppose, theoretical reasons behind why we would want to take advantage of Bayesian inference or Bayesian thinking in general? There's two key components here that I really want to emphasize or to focus on. So first is this idea that in general, we do have more knowledge than what we have just observed directly in front of us. You know, this idea about learning is that you come to a situation with pre-existing experience, ideas and knowledge, and then based on what you observe in that situation, you update your internal model about how the world works. So it's this process of prior information, updating that with things that you've seen to have a then more well-rounded, more complete idea of how the world works. And then to add on to that, there's this idea that just because we have observed some things or just because we have some prior assumptions about how the world works, we also don't have exact certainty in those things. So a really powerful tool with Bayesian inference is this idea that you can encode and quantify and really reason about the level of uncertainty in your model. So to motivate this from a bit of a different perspective, I'm going to present it in terms of personality and career, because my background is in psychology, and that's where my brain normally goes first. So an example you might have seen, if you've seen some YouTube videos by Grant Sanderson, is this idea of predicting whether someone is a farmer or a librarian. So in this hypothetical situation, you've met someone called Avery, and you're asked to predict whether Avery is a farmer or a librarian. This is a completely false dichotomy. In this situation, they are only one or the other. There aren't other careers to choose from. So what kind of observations and assumptions do we have at this stage? Well, really, all that we know is we have a person and we have to predict their career. We don't know anything about them. We don't have any ideas about the world in which they work. So really, all that we come up with is that they could be either, and we don't really have any confidence or any certainty in our conclusions about which one that they are. So, yes?
What if we know there are like 4 factors,
Are you reading ahead in my slides? So the question was, what if we know that there are more farmers or more librarians? And that's exactly the kind of thing that we'll be covering in about 3 or 4 slides' time. So if we wanted to sort of visualize this kind of graphically, this idea of uncertainty, it could look something like this, where we've said that really we know nothing, we assume nothing, so every probability of Avery being a farmer is equally likely, and we don't have more certainty about any particular probability than the other. We don't know for sure whether Avery is a farmer or a librarian, and we have no confidence in any prediction we might make. So what would happen if we were to add a little bit more information? What if Avery told you a little bit more about themselves? So we update our model of no observations and no assumptions, and now we add a little bit of data. We add this idea that Avery prefers structure and organisation. Avery is often described as quiet and introverted. Now, in the traditional analytic framework, this would be described as our likelihood. We're bringing no prior observations, we're bringing no prior information into our model. We're just saying, we've observed this data, what conclusions are we making based on our observations? So naturally, we predict that Avery is more likely to be a librarian than a farmer. Would anyone like to hazard a guess about how confident we should be in this prediction? And any reasons why we might or might not want to be confident? It was kind of touched on a little earlier with that question. All right, so it's this idea that just because we have no assumptions doesn't necessarily mean that there aren't external factors that we aren't observing. So if we, again, sort of graphically depict this idea of how our confidence and our certainty has changed, again, I'll just preface that a lot of these images are completely arbitrary. I'm not implying any particular posterior prior It's just demonstrative. So after we've observed this new information about Avery, we now believe that the probability of Avery being a farmer is much smaller, because based on the personality traits that we've heard about, Avery sounds like they would be much better suited to library work, and that's the kind of thing that they would prefer. So now we believe that the probability of being a farmer is low, and we have more confidence in that probability as well. We can see our uncertainty decreases throughout these ideas. But we're Bayesians, and there's more to this picture than just what we've observed. So what if we had some idea about the probability of just any given person being a farmer, if we just picked someone off the street? So in this case, what if we had some ideas about worldwide what the occupation statistics were? Overall, anyone in the world, are they more likely to be a farmer or a librarian? And if we look, we see that there are dramatically more farmers or people in agriculture than there are librarians around the world. So on average, the probability of someone being a farmer is much, much higher than their probability of being a librarian. So regardless of someone's personality traits, both their sort of social structures, expectations, things like that, they're going to affect career occupation choices. And these are all external bits of information that we want to encode and include in our model and include in our reasoning about a particular outcome. So based on this idea that on average throughout the world people are much more likely to be farmers than librarians, we're now going to update our model, and we would now predict that Avery is more likely to be a farmer than they are to be a librarian. But this raises another key question. So we've added prior information, we've added prior knowledge, but how much certainty do we have about this prior information? Would anyone like to guess how confident we should be about the influence of these worldwide statistics? How much influence do people think they should have? A lot or a little? Yes?
It depends on how much data we would have.
So the answer is depends on how much data we would have. In what way?
So, like, you're using the prior, but then you also have some real data in terms of like populations.
Absolutely. It is also about the balance of the data and the prior. But yes, so framing it in terms of a prior, what would you say about this prior, about the average probability of being a farmer? Would we want that prior to have a lot of influence, or would we only want it to have a small amount of influence? What do you think?
Is it harm to have a lot of influence if you have enough data?
Yes. So the answer was it doesn't harm to have a strong prior if you have a lot of data, and that's exactly right. We'll also be covering that in just a second. Was there another hand? Yes?
I have a question. Why is it that we have classical inequity with especially not with the number of farmers and librarians and farming? Is that something we know already?
Yes, so it's this idea of that. So the question was why are we including these assumptions about farmers and librarians? Are these things that we know already? So part of developing a prior for a model is that you want to look at aspects of the phenomenon that you're modelling and look at expectations around what kind of relationships will be present, what kind of population characteristics are there. It's this idea that there is information that you haven't directly measured, but that you can introduce based on external knowledge, prior research and things like that. Perfect. So to come back to this idea about the level of influence of this, just because these are worldwide statistics, we're averaging across everyone throughout the world, and we're ignoring the fact that there's pretty significant individual difference between countries, regions, suburbs. Someone in a city is going to be much more likely to be a librarian than someone growing up in a very rural country. So just because we have a prior around a particular probability, we also need to encode our level of certainty in that prior. So if we now consider the global probability of being a farmer, we're going to adjust our internal model, adjust our reasoning to say, well, we think Avery is more likely to be a farmer. But because we don't know where Avery lives, we don't have a lot of confidence to say that we're going to allow this prior to have a lot of influence. We know there's some information to be gained by including it, but we don't want it to drive our reasoning and our conclusions. So what if we knew more about Avery? What if we could add a little bit more information? So if we had some more data, for example, we have more observations. So we now have a much stronger observed likelihood. We've now seen that Avery loves books and Avery spends most afternoons at the library. So again, this is providing much stronger observed information that we would conclude that Avery is likely to be a librarian, regardless of the fact that worldwide, on average, people are more likely to be farmers. So we now update our internal model now that we have more information. We give more weight to this observed likelihood because just because we have this prior, we don't have a lot of certainty and we don't want it to influence our conclusions and our predictions by a greater amount. So this then raises another question. What would happen if that prior information was influential? What if we did have a lot of certainty in our prior? What would that look like? So you might be saying, well, if someone grows up in the city, they're really not likely to be a librarian, really not likely to be a farmer. So what if I told you that Avery was from Denmark in Australia? That's a real place. That's where my dad grew up. Not a farmer. We don't include that in the prior, though. So Denmark is a small country town about 5 or 6 hours drive south from Perth, my hometown. Yes? Yeah. Say that again, sorry? Yes. No, sorry. The speaker is I've truncated the top of the plot, so these densities do transmit up, but just to make it so we can see the full range a bit easier, I've truncated it, sorry. Does that answer the question? No worries. All right, so if we consider that, so if Avery told you that they grew up in Denmark, still hear laughter, not to take that personally. So Denmark is a small country town. They only have a population of about 6,500. Their primary export is agriculture, beef and dairy farming, and a very, very strong wine region as well. Now, in Denmark, there's only one library, and they already have 2 full-time librarians that have been there for decades, and they're not likely to leave anytime soon. So we now have some very, very strong prior information that regardless of Avery's personality, regardless of what Avery wants to do, the system and the social structures just aren't there for him to be a librarian. So we now take this idea that we have a very, very strong prior to encoding the model to say that regardless of what we've observed, there needs to be much stronger observed information to override this fact that really there isn't much opportunity to be a librarian in Denmark. So now we have this sort of internal model that says, regardless of Avery's personality, the Australian volume. So we have this model that says, regardless of Avery's personality, regardless of what Avery wants to do, there's not really much opportunity or chance for him to do that. There is a very low probability for anyone in Denmark to be a librarian. So because we have this very, very strong prior, if we wanted to change our prediction and change our level of certainty in our predictions, we would need more and more observations. We would need to know, maybe Avery's parents are the librarians. Maybe we know that the librarians have told Avery that they're retiring soon, or something like that. So it's this idea that you have certainty both in your observations and in your prior information, and it's the balance of those two that you encode in your posterior and your conclusions. So the key takeaways here is that when we're talking about Bayesian inference, the key things are that we want to consider both the data in front of us, our observations, our likelihood, but also we want to consider this external prior information that is available. Now, this prior information, it doesn't have to be theoretical, library statistics, population statistics, prior research. It can also be model-driven. You see a lot of very strong prior information used to identify particular statistical models and things like that. Not something we'll cover today, but I'll touch on it briefly later on. And it's also this idea that the strength of confidence or certainty that we have in our conclusions from our model, they also influence our strength. It also influences the strength of our confidence and certainty in our predictions. So if you have a strong prior, you have a lot of certainty. You have strong observations, you have a lot of certainty. If you don't have either, then your predictions are very uncertain. And we've also seen that if one of them is weak, the other one is going to dominate your conclusions and your certainty. So if we have a very weak observation model, but very strong influential priors, it's the prior that's going to drive our conclusions and our confidence in those conclusions. So it's really key to consider both aspects when you're building your models and developing your inference. So if we now move from this a bit psychological, abstract sort of thinking and bring it back to, I suppose, the rigorous specific. Sorry, yes?
I have a question because we always talk about certainty of something.
Mm-hmm.
So my question is, how do you then encode this in a probability distribution? Is it like more uniform if you're less certain?
Yes, so if we consider here, so actually no, it's probably a bit clearer to go to this slide. So there are two ways to sort of encode that uncertainty. So the key one is if we have a look at our prior knowledge, the probability of someone being a farmer. Now, in both of our examples of this prior knowledge, so one was worldwide population statistics and one was Denmark population statistics, both of those come out to pretty much the same conclusion, that someone is more likely to be a farmer, but we have much more confidence and certainty in the one from Denmark. So when we're assigning a prior or a prior distribution to this information, we would have that prior still centred in the same place, but that distribution would be much narrower when we're talking about someone from Denmark, because we know that isn't going to vary around that prior value that we think it's going to be. We'll touch a little bit more on that later, but yes, so this idea of certainty comes from the distributions that we're going to be reasoning about in our model. Yes. Did anyone have, were there any other questions about this idea of Bayesian inference and certainty and things? Yes?
Isn't it already an observation about Avery that they are from Denmark?
Well, that's a very good question. So the question is it already an observation that they are from Denmark? So if it was part of your data collection process to record where someone was from and you modelled that as part of your outcomes, then it would be. But if it's just that you're conducting a study completely within Denmark, you're not going to be recording where someone's from, but you want to account for the fact that everyone from Denmark is likely going to be affected by this same process. Does that make sense? Yeah. Perfect. All right. Any other questions? Oh, yes, one more.
Is there a common way to see where should be rotation other than its computation?
Good question. So the question was there a good rule to determine when you should go Bayesian or not? It's a very controversial question. My boss would probably want me to say, always go Bayesian. But reality is there's two decisions to make. So one is you want to take advantage of this idea of prior information, external information, and encode that in your modelling, because as we see, it can make a strong difference in your conclusions. And that becomes especially important when you work with very complex models. So, for example, this large p, small n, so you have a lot of predictors but not a lot of data. Statistically, you don't have a lot of information there to identify that, so you have models like lasso and things to regularise it down. But when you work in a Bayesian context, you can introduce this additional information as part of your prior. You can provide a similar regularisation, or you can say that I think it's quite likely that this value is going to be a bit higher, and you can encode some knowledge about that. On the other hand, Bayesian estimation can make a lot of problems much more computationally tractable. One example is, so with my background in psychology, a lot of the measures that we give people are scored on a discrete ordinal scale. So when you ask about someone's experiences of depression, it's 0, 1, 2, 3, rarely to always. And when you model those using a latent variable model, like was covered on the first day in Celia's topic, where you have these unobserved constructs, for example, depression, and these influence your observed measurements of, wanting to get out of bed, energy during the day. Statistically, when you want to estimate a latent variable model with discrete outcomes, you have to marginalise the latent variable out because you can't directly model it. With continuous data, it's quite trivial, it's quite easy. For discrete data, every additional latent variable is an additional dimension of integration, so it becomes computationally intractable very, very quickly. In a Bayesian estimator through MTMC, HMC, it's much more computationally feasible. So that was a very, very long-winded way to say that you have theoretical reasons, and you might also have computational practical reasons for going Bayesian.
Is it usually the case that the most restrictive way to go Bayesian, like the reason to not go Bayesian, is not just computational expense, but also do you have a strong prior? Because if you don't have a strong prior to start with, then maybe you're too far away from.
You can have a weak prior.
Yes. So the question was, one of the reasons to not go Bayesian was, what if you don't have a strong prior? What's the point? The point there is that you also still get some idea about uncertainty, and we'll touch on that exact situation a bit later on of not having a strong prior, but still wanting to quantify our uncertainty in our modelling. Perfect. So if we tie this example back to the actual components of Bayesian inference, we have our posterior on the left here, which is our goal, which is this idea of saying, what is this probability of Avery being a farmer? What is it? How confident are in our estimation of what it is, that level of uncertainty? And we say that this is proportional to our observations, our likelihood. So what information do we have about Avery that contributes to our internal model? And then, of course, our prior information and our level of certainty in that prior information. But of course, this raises quite a large question. How do we take these observations and some prior knowledge and assumptions and actually turn that into a model? How can we be confident that we've made good choices or the right choices? There's never a right choice in models. There's a very famous quote that all models are wrong, but some are useful. So really, you just want to be able to be confident that you've made good choices, robust, defensible choices. And that's a big focus of this idea of Bayesian workflow. Pardon me. So what's Bayesian workflow? Why do you need it? So as we've seen, Bayesian inference is pretty powerful. You can add extra information, extra certainty, and really add a lot of richness to your modelling and your inference. But it's also very complex. You both have multiple options for how you specify your observation model, how you specify your prior model, but you also have a lot of ways to specify the same observation prior. And different ways that you specify it can lead to different computational issues, different levels of certainty, different results. And that's something that we'll touch on explicitly later as well. So because of this complexity and because of this uncertainty in quantifying uncertainty, that was a pun that you can laugh at if you like, this leads to a series of very ad hoc decisions. It's just people deciding what works at any given time and just throwing away a lot of models. We don't have a robust system of what's this process of how do I know what to do next, when do I know when to stop, something like that. So we need something that's systematic but flexible. So if we take a step back and sort of think about what happens in Bayesian modelling, really we have three key stages. So one is this stage of actually building and defining your model, taking your observations and your data and turning it into a model that you want to estimate and make inference on. Then once you've done that, you make your inferences based on the model, and then you should also be checking the quality of those inferences. So you check your model, you check estimation issues, specification issues, and then if you need to, improve your model. So naturally, each of these stages covers quite a lot of steps because there are multiple ways that models can go wrong, models can be specified. And it also means that when something happens in one stage, you might have to return to an earlier one to revise your approach. So this is a complex, but it's an iterative process. So if we think about some of the key principles of a Bayesian workflow that we want to take advantage of, we want something that is systematic. We want to reduce the level of ad hoc decision making that a given researcher or a practitioner is going to have to apply. So that's a big part of the work that Archie Vetteri's group works with, is this idea of what are some recommended evidence-based decisions or a decision process to follow as part of a Bayesian workflow. But also we want this to be flexible. Every model is different, every model is going to work or fail in different ways. So if you prescribe the exact same procedure for every modelling process, it's going to work really well for some and really terrible for others. So we need something that's going to be still rigorous and systematic, but also has the ability to change with a different problem. And then finally, a really, really key thing, particularly in fully Bayesian inference, is this idea of we want something that's practical. So your time is infinite, your resources aren't infinite. So if you're working with very complex MCMC models, they might take days to estimate, or they might require spinning up AWS instances that cost a lot of money for the business. So what we want is a robust process that's going to reduce our unnecessary effort and time. And a really key concept that gets emphasised here is this idea of failing early and failing fast. So if there's something wrong, you want to find out about it before you've been estimating it for days. And if it is going to fail, you want it to fail early on in a given step. So you may have already noticed that throughout the past couple of days, you've actually seen some examples of Bayesian workflow and some Bayesian workflow steps. One of these is Box's model, popularised by David Lay. And you can see that it follows roughly a fairly similar journey of we've got our data, we build our model, we make our inferences, we criticise, so we check our model, and then we return to the start. But then this also runs into that same issue of this is a very non-specific workflow. How does a researcher know what to do in each step? What do they look for? What does it mean when something goes wrong? And if something goes wrong, what do they do next? That's obviously not something that is very easy to demonstrate in a small slide, and it was something that was the paper written by Andrew Gelman, Archie Vetteri, and some colleagues a couple of years ago, where they proposed a much more rigorous approach to Bayesian workflow, a very systematic set of steps to follow right from the start of having an idea of your model to building it, estimating it, and checking it. So they covered the key application of different diagnostics at different stages of the model building process, so you can fail early. And also identifying computational issues, because there are a lot of different ways that an MCMC sampler can fail, and some ways that aren't immediately obvious. The tricky part there is that because there is so much to cover, so much that can go wrong, so many steps to follow, it turns into a bit of a behemoth of a process. While Box's loop is a bit easier to pass, I always find it funny when I look at this. So we have here a very complex set of steps to follow. Don't worry about trying to read all of them now, otherwise I'll have to leave the room for 10-15 minutes. We're going to be stepping through each of these steps later on in our practical sort of process. All right. Now, before we get into that, we'll just very quickly cover some of the basics of computation Bayesian inference, because we have multiple steps that are specifically around checking for computational issues, checking for issues that might, diagnostics related to the computation. So let's touch on what those can look like. All right, so if we return to this construction of Bayesian inference, we have our posterior distribution, and we want to use it to make some sort of inference. Normally these are expectations, what's the mean, what's the variance of our distribution. In many, many cases, you can't specify this in closed form to work with efficiently. Those closed form specifications being the conjugate models that you would have heard earlier. So because we can't do that, we need a numerical approximation. In this case, Markov chain Monte Carlo. So MCMC is a very powerful method for numerically computing expectations over complex or difficult distributions. The key component that it's based on is this idea of a Markov chain, which is a sequential set of samples, and each time you take a sample, that sample informs the next sample that you take. If you have constructed this process of sample to sample properly, using what's called a Markov transition, after enough time, that sampling process will quantify your target distribution. I'm not going to cover the different Markov transitions, it's a bit beyond the scope, but if that's something you're interested in, that's the word to Google, a Markov transition. When we talk about our Markov chain Monte Carlo estimate, it's the expectation of our target function over the samples from this distribution. So to put it a slightly different way, we have a target distribution that we want to make inferences about. In this case, it's our posterior, the probability of Avery being a farmer. We construct a Markov chain, and we run it for n iterations. We take n sequential samples exploring this target distribution. And then we construct this estimate. So you'll often see this notation, f hat of n, which is saying our estimate, of our function, which is based on n Monte Carlo samples. And what can be proven is that as we take more and more of these samples from our distribution, as our Markov chain gets longer, assuming that it's parameterized correctly, this estimate converges to the true expectation over that given distribution. Right. But what does that look like in practice? So let's say, for example, you had a bivariate normal. On the left here, we have our density, just displayed here in 2D as a contour plot. And on the right here, we're going to be tracking the level of bias in our Monte Carlo estimate as a function of the number of samples throughout our Markov chain. So here the E of f is our true, and the f hat is our estimate. So when you run a Markov chain, you don't know where your probability mass is. You don't know where in the parameter space it's going to be. So you'll start your Markov chain just from a random point, and as part of the process of the Markov chain, it finds your probability mass. So this means that in our estimate, the most bias is present at the start because there are some samples of that Markov chain that aren't from our target distribution. We'll cover a little bit later on about how that's normally dealt with. Spoiler alert, they just throw them away. So the most bias in your estimate is present earliest while we're finding our distribution. Now we see that as our Markov chain finds a probability mass and begins to explore it, that bias then reduces as the iterations increase. And the longer that you run this Markov chain for, the more that bias reduces, the closer your estimate gets to the true expectation. So 2 things to emphasize there that we'll be coming back to later is there's 2 sources of bias present in this process. So first, it's finding the probability mass of making sure that your expectations are across samples that are from your target distribution, and it's fully exploring the probability mass. Because in this example we have a 2D bivariate normal, very simple, very easy to explore, but what happens if your posterior is geometrically pretty nasty and hard to find, hard to explore? While asymptotically MCMC will fully explore it with infinite iterations, your computational resources and time aren't infinite. So what we need to do is to adapt MCMC, adapt our Markov transitions to be a bit more effective in finding and exploring this posterior mass. And where this comes in is Hamiltonian Monte Carlo. So you'll remember from the probabilistic programming workshop, they talked about these 3 generations of languages, and the early ones being things like JAGs and bugs, often not scaling well. So as you add more and more parameters to your model, your parameter space increases in dimension, and that means that your probability mass becomes increasingly sparse. It's spread across this parameter space in very difficult ways. So what we need to do is to have something that tells our sampler, our Markov transition, the best way to go to find this probability mass and how to efficiently explore it, even if it's taking a very tricky shape. So the principle of Hamiltonian Monte Carlo is it takes your probability density function and uses the gradients of that to guide where the sampler should go. I'm not going to go into how exactly that works because that's a whole other lecture, but if you are interested, Michael Betancourt has an excellent paper about a conceptual introduction to Hamiltonian Monte Carlo, where he talks about the physical sort of motivations of how the process works. So while HMC works very, very well, it requires the specification of tuning parameters based on how we use those gradients to explore the target distribution. Now, in many cases, these parameters are quite unique to the posterior at hand, and they're not easy for you to know in advance or to know without iteratively trying and adapting your model. So while there was a lot of potential for Hamiltonian Monte Carlo, it didn't receive a lot of widespread use. What was then adapted was this idea of the no U-turn sampler, which is a modification of the HMC algorithm to automatically tune those parameters to adapt your sampler to the best parameters or close to the best parameters for HMC. Right. And it's this no U-turn sampler algorithm that was popularized by Stan, which is the probabilistic programming language we'll be covering today. Right. Does anyone have any questions before I move on to Stan in general? I haven't. Oh, sorry. Yes. No, it won't. Sorry, but I'll put it in the Slack channel so you can find it later. Sorry. The question was the reference for the Betancourt paper. So I'll post that in the Slack for everyone to look at afterwards. Yes. Yeah. Yes, that's also in Betancourt's paper as well. Yeah. And for a particular author, you'd be looking for Matt Hoffman. He was one of the big names that helped introduce the no U-turn sampler. No worries. Anything else? All right, perfect. Alrighty, so what is Stan? Now, I'm very biased because I am a developer for Stan, so it's always going to be my go-to. So Stan is a probabilistic programming language. It provides this MCMC sampling both by traditional HMC and also by this adaptive no U-turn sampler. It provides gradient-based optimization, automatic differentiation, variational inference, and more recently, Laplace approximation was added. So because Hamiltonian Monte Carlo relies on this idea of needing the gradients of your target function, we need to have a way of building up a probability density function and also calculating the gradients of that probability density function. So Stan is built on a C++ auto differentiation library, which as you construct a model, as you call functions, it automatically builds those gradients for your function. So when we talk about a Stan program, really just think of it as a tool for specifying a joint log likelihood or a joint density function, which is your likelihood and your prior. So how does that look? So Stan is specified in blocks. There's 3 key blocks I'm going to cover now, and then 2 more that I'll cover when we get to the practical section. So we have our data, our parameters, and our model. Fairly self-explanatory. The only difference is the model part is where we specify our prior and our likelihood. Our parameters are where we specify the random variables that we're going to be using as part of that prior and likelihood. And our data is where we specify the fixed quantities that we'll be passing for our model to use. So, a quick example of how to put all of that together. So let's say you have a very simple linear model. You have an unknown mean and standard deviation. Who can tell me what the data in this model is? What would we be specifying for Stan? No. What fixed quantities, what are our known quantities based on this that we want to be including in our model? What are we modelling? Close. So in this model, we have 2 pieces of data. We have the number of our observations, and we have our observations themselves. We can process them for more information, sample means, sample standard deviations, but that's not what's being estimated as part of our model. We're just looking at our observed outcomes, and we're estimating a mean and a standard deviation. So as part of this model, we have an unknown mean and an unknown standard deviation. So our parameters are our unknowns. We have 1 mean and 1 standard deviation. Now Stan has some quite helpful constructions. So one of them is this idea of constraints. So you can see here that we've specified a lower bound. Lower is equal to 0. So you can specify a constraint on your parameter like this, specify your prior as normal, and Stan will take care of this process of making sure that the values only take positive values. So on the back end, it transforms your samples to an unconstrained space, so negative infinity to infinity. Those get sampled by the sampler, and they're transformed back to the range of constraints that you've specified. So in this case, 0 to infinity. And part of that process involves needing to add a correction to our sampler. So, sorry, yes? Yes, exponential transform to make it all positive, yes. So this process is pretty much the same idea as normalizing flows, these invertible transforms with a correction for the transformation. All right, so now that we have our parameters and our model, does anyone want to guess what our priors are going to be?
We don't have a particular uniform in this case. We don't have much knowledge about the priors.
Well, I suppose the question is what are our priors here? So we've got our random variables, the things we want to estimate, mu and sigma. What in this model, skipped ahead there. Well, there goes that. So in this model, we have our random variables, our unknowns, and we're saying that they are distributed with a normal and a half normal. So these are our priors. So when we specify them in Stan, Stan parameterizes the normal in terms of the mean and standard deviation. So not the variance and not the precision, which for people that came from JAGs or bugs can be a bit of a adjustment. All right, yeah, so we have our priors here. So our two unknowns, and they're given these priors for a normal and a half normal. Now, you might note there that I've said a normal and a half normal, but the Stan code is the same for both. They're both just a normal. Well, this is because we've specified a constraint on sigma. We've said that sigma can only be positive. So that means that our prior is then induced to be a half normal, only positive. You'll see the same thing for things like the Cauchy priors or things like that, where we use the constraint to induce a half distribution. Yes? That's a good question. So the question was, how do we encode it to include 0? So there's two ways. So pretty much the idea is that you would never take positive values, but it would go down to 0, right? So it is a tricky one. So what I would do computationally is this idea of that you're going to set the minimum as the smallest possible number that can be numerically represented. So it's going to be as close as possible to 0 that the computer can represent. That will allow you to take the smallest possible value before it becomes negative. Yeah. Bit of a computational trick rather than a statistical one, though. Right. Do we have any other questions about the syntax before we... Yes?
Yeah, one also regarding the half-normal distribution. How does the mapping work after the constraint? Because I assume you cannot map the complete left-hand side to the 0 point, because we would have a higher probability mass than it is supposed to be.
Yes. So that's a very good question of this idea of putting a prior when we have a lower bound of 0. Yes, so it does result in more probability mass being pushed up against the 0, pretty much. Which is also part of the reason why we recommend prior and posterior predictive checks, which we'll cover in just a sec. So just because you see a lot of models using this half-normal or a half-Cauchy approach, it is still important to be checking that it works for your data, especially with constraints like this. Well, any other questions? Yes?
You say that the sigma is half-normal, but it's stated here as normal, right?
Yep, so that was what I covered before, of like, because we have the constraint at 0, it induces a half-normal when we specify the prior. Cool. All right, so now we have our parameters, and we've specified the priors for our parameters. What's our likelihood in this model?
Okay, but
we have no find this
yeah, but
Yes? Perfect, yes. Product of normal densities over our observations. Another way to describe it is independent normals. So each one is independent of the others, which we would represent in Stan using this notation. So this is slightly different to what you'll have seen in something like Pyro, where you have specific syntax for when you're working with either scalars or multiple values. So this is the plate syntax that Pyro used. In Stan, our functions and distributions, or at least most of them, are vectorized. So they will take multiple values, either for the outcomes, for the parameters, and they will efficiently use those. I'll touch a little bit on that later. But it's just to say that when you see this y distributed normal, so outcomes, it's saying that each element of y is given a normal likelihood with a mean of mu and a variance of sigma. This would be the same as specifying that the vector of y is a multivariate normal with an identity covariance matrix. But never do that in Stan because it's less efficient than independent normals. Yes? Sorry, yes. Standard deviation sigma, sorry. Thank you for catching that. Did we have any questions on the likelihood section? Yes?
Now have like semicolons behind two lines, but not behind the other one. What's the syntax?
Oh, you've got my syntax error. That's terrible. They're going to take my name off the website now. Damn. All right, good catch. Don't copy and paste my code is the conclusion there. All right, were there any questions that don't make me look bad? All right. Cool. So the next step would be to talk a little bit more about Stan, but just keeping an eye on the time. I think this is probably a good place to stop for a short break. Have covered a lot of content, so you might have other questions you want to ask as well. So if we stop for 10 minutes and say we come back at 2:20, and then we'll get into the rest of it. Thanks, guys.
Well, because I have been working on a paper from the main lead of Stan. But this was before this guy, Aki, the guy from Finland. This was before he even started performing. And he has developed a model there, and then looking for it.
Alrighty, so it's time to get started into our next section. So far we've talked about what a Stan program looks like, how we would take a particular model, a particular observation and likelihood, and how we would specify that using Stan. So some of you might have already noticed a few differences from things like Pyro or languages that you've already learned. Stan does have a few of its own little quirks. So one of them is this idea that Stan requires on strong static typing. So this means that every variable has to have a type, and after you've declared what a variable's type is, it cannot change. So you can see here we've declared a continuous real, an integer, and a vector. Later in the program, we can't redeclare y as now being an integer. We can't change its type later on. We've also seen that Stan allows for easy vectorization. You can use the same function, same distribution syntax that you would use for scalars as you would for containers, working with vectors and matrices. Now, this is very important because it allows you to reuse expensive pieces of computation. Consider, for example, a multivariate normal. That requires inverting a covariance matrix. If you have multiple multivariate normal outcomes, you don't want to be computing that inversion every time. If you pass all of them at once, it computes that and it can then reuse it for every observation vector. It also allows Stan to more efficiently handle these large inputs. I'll talk about why in just a second. But a really key thing to talk about here is this idea of Stan relying on automatic differentiation. So this idea is that whenever you call a function, as you build up functions, Stan has to build a graph of every time a function has been called so it can propagate those gradients back to the original variables. If you have multiple function calls, you're looping over each element, you're adding n different calls to that graph. If you use a vectorized call, Stan knows, well, this only happens once, and we can very efficiently propagate it back to every input. A really key thing that trips up a lot of people when they come to Stan is this idea that Stan is a compiled, not an interpreted language. Can I get a show of hands of the people that know what that means? Very good, brilliant. So when we talk about PPLs like Pyro or the classical JAGs and bugs, These are interpreted languages. We specify our model, our commands, and we give them, and they just run as is. Stan, on the other hand, has to be compiled. So you take your Stan model, Stan then translates it to a C++ program, and that's compiled to an executable, which is then executed. On the surface, that sounds like a lot of unnecessary steps. Why would we do that? But there are benefits and there are drawbacks. So compiled languages can have some pretty significant benefits. So on one hand, it reduces a lot of the overhead. You only have to build a program that does the bare minimum of what you need. Compilers are very, very good at optimizing your code when it gets compiled to machine code. A lot of work and developer time goes into compilers identifying inefficient code or particular pieces of code that can be combined and move around to give you the same results in a much faster way. For example, the Clang C++ compiler is very, very good at identifying mathematical points where it can be optimized and reduced to simpler functions. It also opens up the possibility of machine-specific optimizations. So each CPU will have different capabilities that are built in, different instruction sets. One of these, for example, is this idea of single instruction, multiple data set, which is where you can apply a particular function to multiple pieces of data in one CPU cycle, rather than requiring a cycle for each element. Sorry. So that all sounds very powerful, very helpful, but of course there are limitations. Compiling code, it takes time, it takes resources. RAM and CPU, they will always be expensive. It also means that if a user wants to use Stan, they need to have a working C++ toolchain. Anyone that's worked with C++ on Windows knows it's an absolute nightmare. I've spent so much of my life helping people get C++ working on Windows, it's awful. So altogether, this really reduces accessibility for new users. It's a high barrier to entry when they're coming from programs where they just write their language already in Python syntax that they're familiar with, and it just runs with no issues. But despite all these things, I think Stan is better than all of them, so that's fine. All right, so stepping back a little bit, what have we done so far? Oh, sorry, yes?
Can you relax any of these requests or requirements with Python wrapper?
Relax the compiled requirements?
Yeah, the coding aspects for C++, you made Python wrapper. I think there is Python.
Yes, so we do have, so for both so the question was, can we relax these compiled language requirements using Python or Python wrappers? The answer is, as any statistician would say, it depends. The wrappers we have at the moment for both Python and R, there are two approaches that they take. So one is that they use existing functionalities in that language for compiling and linking C++ code. On the other hand, you have just pure wrappers, which delegate to the command line interface to Stan, and we'll be looking at that later. The difficult part is there's only so much that you can do ahead of time. So because Stan is a compiled language, when you write your program and it's compiled and you compile it, after that it can only do what the program has been written to be able to do. So one workaround that you see a lot is people will write very, very large and very flexible models. For example, in the R package, RStan ARM, where these models are built to be able to take multiple different observation families, different values of priors, different combinations of linear predictors. And the syntax is coded in such a way that, depending on the data that you pass in, it can estimate wildly different models. So using that approach, you can compile one very, very large model that you can then apply in many, many situations. But then again, you come back to that trade-off of that's a very large model. It takes a lot of space to install. The first time it gets built and compiled, it takes a lot of memory. and it runs a little bit slower than a pure optimized model. But that's about as much as we can work around the compiled limitations at the moment. People that are familiar with compiled languages will also be familiar with this idea of a just-in-time compiler, where the code can just be compiled and executed at the same time. While there are some while there are some just-in-time compilers for C++, the kind of code that we use in the Stan library isn't compatible with that because we use what's called template metaprogramming, which is a very, very abstract way of writing code that allows us to apply it to multiple different data types and data structures while still being strongly typed. And that really doesn't play well with just-in-time compilers. Right, do we have any more compilation questions? Yes?
So does it mean it's very difficult to extend if you haven't thought through the process?
I'll just say that again, sorry?
If you have a model, let's say, and you haven't thought through like all the extensions and possibles for it, I want to extend it, does it make it very difficult to extend it? Let's say I had to write a whole database.
Exactly, that's a very, very good question. So the question was, does that make it difficult if I want to extend a model that I've already written, add additional parameters, variables? The answer is yes. You then just have to compile another model. And this is a really key part of our Bayesian workflow sort of idea of, because this is expensive, building models, you don't want to be doing unnecessary model building and model testing. Pardon me. That's something we'll touch on a little bit as well. Cool. Any more questions? Brilliant. All right, so far we've established why we might want to use a Bayesian model. We've talked about this idea of Bayesian inference and what it really adds to modelling. We've touched on the concept of a Bayesian workflow, what we want to achieve, sort of the principles behind a workflow. We've covered a lot of these, we've covered some of the key statistical methods. So remember, this is the MCMC and these two sources of bias, finding the distribution and exploring it. And we've also done a crash course introduction to Stan. But this is all a little sort of abstract. We've just been talked at for an hour and a half, and this is meant to be something practical. So how do we put this into practice? How is this something that you can apply? So again, because my background is more psychology and medicine, we're going to be talking through a problem of a randomized controlled trial for a treatment for epilepsy. On a much smaller scale than a lot of data scientists are used to, but this has been my bread and butter for years. So in this case, we have a randomized controlled trial for a new drug, 59 participants, fairly even split between treatment and control, multiple assessments, and we've also recorded how old each participant is, and before they started the treatment, how many seizures they were having during the week. And for our outcome, we want to know how many seizures did they have since the last time that they were assessed. So ideally, for patients that are taking the treatment, they will be seeing smaller seizures than they will be seeing a smaller number of seizures than their last visit. So, as a bit of a jump scare, remember our workflow. So we have many, many steps to work through. But it becomes a little bit more feasible, a bit more tractable if we break it down into smaller steps. So the first step that we have to follow is this idea of picking an initial model. And this doesn't mean just statistically, it also means having some sort of a hypothesis about what we think our outcome is, what we think we're modelling, what we want to achieve. So we have our outcome, which is the number of seizures at each assessment, and we have our predictors, whether they're in the treatment or not. We have their age, and we have the number of seizures they were having at the baseline. Now, when we build our model, what do we think are going to be the relationships between these and our outcome? What do we specify? How do we build our model? This is assuming a little bit of prior knowledge that you might not have, but in this instance, we would say that the researchers do not expect age to affect the efficacy of the drug. So we don't care, we don't believe that the age is going to be different between, we don't believe that the effect of the treatment is going to be different depending on the age of the individual. But we do expect a greater response to treatment if they're having more seizures, because individuals that have more seizures, they have more that they can reduce and they can change. If someone starts with only 4 seizures, the greatest amount they can reduce is by 4. But if they're starting with 20 seizures, there's a lot more opportunity to reduce. So we would expect that patients that have a higher baseline level of seizures will show a greater response. So what we want to do is look at a separate effect for baseline seizures between the treatment groups. And for those of you familiar with these kinds of models, that's an interaction effect. So based on this, what model do we have? Now, you remember from your earlier workshops this idea of a Poisson distribution. So because we're modelling counts of an outcome, a very common model is the Poisson. And remember, the Poisson is parameterised by a single parameter, in this case lambda, which controls both the mean and the variance of our outcome. We'll come back to that later. So for our model, where we want to model the effect of predictors. So for those familiar with linear models, this is our linear predictor term alpha plus our covariates and beta. When we use this in a Poisson context, we need these to be positive because if lambda is specifying the mean of our distribution, well, a count can't have a negative mean for its rate. So we use commonly what's called a log link. So we model these things on the log scale and they're exponentiated when they're passed to the Poisson. So that is our likelihood distribution. And our predictors, we have the treatment group, we have their age, their baseline seizures, and we also assume, or we want to test, whether the effect of the treatment differs depending on the number of seizures they were having at baseline. This is our interaction term. Right. Does anyone have any questions about that model before we jump on to priors? Brilliant. Okay, so priors. So a question that came up earlier is, what do we do if we don't have informative priors? What's the point of a Bayesian analysis? In this case, we can use informative priors to still allow us to estimate our uncertainty, which can be quite important, especially in a medical trial where we don't just want a conclusion, we want to know some confidence in that conclusion. Now, if we don't have informative priors, what do we do? So for a long time, a very popular approach was using so-called uninformative priors. You'd say, a uniform from negative infinity to infinity, or a normal distribution with a standard deviation of 10,000 or 100,000. But remember what we talked about, where if you don't have strong data, your prior is going to have a lot of influence. So if we have a small sample size and we're using a prior that implies that values of 10 million are possible, well, that prior is going to have a lot of influence on our conclusions. So this is one of those cases where it's very important to consider how much certainty am I encoding with a prior in comparison to the strength of my data. So this is where the recommendation to use weakly informative priors come in. So we don't specify information about a particular value, we just specify information about the range of possible values. So another way to look at it is, you're not providing certainty about a particular outcome, you're just limiting your amount of uncertainty. So you don't know what the effect of the treatment is going to be, but you know that it's not going to reduce the number of seizures by 10 million a week. So we use a weakly informative prior to reduce the range of values it can take, to regularise them to something that's feasible and possible, to reduce the impact that that has as part of our estimation. So how would we decide that? Well, remember we're modelling our outcomes on the log scale, which means that our coefficients are not additive, they're multiplicative. So if someone has a beta of 0.1, we exponentiate that to 1.105, which means that for every 1 unit increase in our predictor, there's a 10% increase in our outcome. In this case, the rate of seizures. So you can see that we don't need a very big prior in this instance to cover our reasonable range of values. So in this case, we'll use a normal 0, 1. So Under that logic, 3 standard deviations, -3 to 3, is where 99.8% we think of our coefficient values could be. So we're regularising our uncertainty and our conclusions to a range of reasonably possible values. And that's not to say that's the right decision either, because that in itself is encoding some particular knowledge. So that's why it's always a good idea to conduct sensitivity checks in terms of your prior and your model. And that's something we'll talk about in just a little bit. All right, so what have we decided? So we've got our initial model, and this is what we've specified so far. We've got our Poisson with our rate parameter, which is modelled by a linear predictor on the log scale, and we've specified these priors for our intercept and our coefficients. Now, at this stage, I'm going to jump over to the notebook that was posted on Slack, and to show you how we would now code this up in Stan and the process of, again, working through this workflow in a practical sense. So I'll jump out of that. All right. So for people that have been using Colab for the rest of the week, you might be expecting this to be in Python. It's not, it's in R, because that's my language. Try not to judge me. So you don't have to make any changes. It'll automatically be set to R. Just be aware of if you try to write your syntax and you try to write Python, it's not going to be very happy. Alrighty, so once we've got a runtime initialized, the first step is to set up parts of the system. So for this analysis, we'll be using the command stan R interface, which really is just a wrapper to the command line interface for Stan. So we don't have to do any sort of special compilation in R, we're just using a wrapper to call Stan. Now, in Colab, it can take a bit of time, this compilation of installing both the library dependencies and command Stan. So I've pre-compiled and built them, and you just need to run this section to download them from the GitHub repo and load them into your runtime session and add them to your installation in the runtime. This will take a minute or so to run. Cool. So while that's running, now in addition to using command stan R, we're going to be using a package called Bayesplot, because a really important part of our workflow is graphical checks. And Bayesplot is a package which provides many different graphical plots for checking different parts of the Bayesian workflow. And we'll touch on some of those in just a second. All right, now that I've wasted enough time, this is finished setting up. So we now have command stan unpacked and ready to use, and we have command stan R installed. For people that want to set that up yourselves, you can just follow the instructions on the Getting Started page with command stan R, and it talks you through the process of installing the command stan R package, and also the process of getting the command line interface set up and ready to call from R. And it will be quite a similar procedure if you're using command stan Py, which is the Python wrapper or Python interface. All right, so now we load our R packages, and we tell our R packages that we're going to be using the command stan that was pre-built and downloaded. All right, so now we're ready to start modelling. Let's have a look at the data that has been collected and the data that we'll be using. So if we load our data set and have a look, we can see that it's set up in the so-called long format. So we have multiple records per person. So for each patient, we have a row for each visit. We have their baseline number of seizures and their age. Now, you'll notice that these values don't make any sense for age and baseline seizures. That's because these have been standardised to a mean of 0 and a variance of 1. With a lot of modelling, you might find computational issues as your predictors get further and further away from a unit scale. So a good step in the checking process can be to standardise them. I've pre-done that because it's not an important thing for us to check at this stage, but just to explain why it looks a bit strange. All right, so let's refresh on our model. We're using a Poisson generalized linear model, a log link for our linear predictor, and these priors. So, how does that look in a Stan model? All right, so there are some things here you have seen before and some things you haven't seen before. So the first one is this array syntax. Now remember, I said that Stan is strongly typed. So Stan differentiates between different types of containers. So there's a difference between a vector and a row vector because that drives particular mathematical transformations, multiplying with matrices. An array is used as a general container which doesn't have an idea of dimensionality in terms of rows and columns. So you can't multiply an array with a vector because just because an array is of the same length, it doesn't have any idea about whether that should be a vector or a row vector. So we use arrays because we're passing in integers. Now in Stan, when you're working with vectors, matrices, row vectors, they're always going to contain continuous real values. If you want to work with integers, you have to pass them in as an array, just a general container. And that's really important here for our outcome seizures because we want to model it as a count. Because Stan is statically typed, if we pass it in as a continuous variable and we try to model it with a discrete distribution, in this case a Poisson, Stan wouldn't even let you compile it to throw an error because the type isn't right. That's very important because we know for Hamiltonian Monte Carlo, we only calculate gradients for continuous values. We can't calculate gradients for discrete values, discrete parameters, because the gradients are discontinuous. So Stan needs to know whether it's continuous or discrete when it operates for constructing functions. So we have our array of outcomes, and you notice that we've passed in 2 or 3 identifiers. So first we have the number of individuals, in this case our 59 participants. We have the number of time points that they were assessed, so in this case 4. So we have 4 assessments per person. And here we have the number of predictors that we'll be using. And remember, we've specified 4 predictors. So treatment, age, baseline, and baseline by treatment. Now we're saying that we're going to be passing those predictors in as a single matrix. So 1 row per observation, 1 column per coefficient. And that makes for much more efficient construction of our linear predictor. So we have our parameters, our intercept, and a regression beta coefficient for each of our covariates. All right, so now we have the second thing that's different, this transformed parameters block. So because Stan has to compute gradients for transformations that are going to be used to construct our joint likelihood, Stan needs to know that if you're constructing a transformation, does it need to compute gradients or not? So the transform parameters block is where you declare and construct items that you are going to use as part of your likelihood and observation, or was where you declare or construct things that are transformations of parameters. In this case, it's a transformation of alpha and of beta. That's distinct from the generated quantities block down the bottom here, because here we're just making predictions from our model. We don't need to use those predictions again back in our model. So by creating our prediction, creating our transformations in the generated quantities block, Stan knows that it doesn't need to compute gradients for anything in there, which is good because it's an integer and it can't. All right. And now you can also see some of Stan's specialized distributions or likelihoods. So rather than specifying a normal 0, 1, we can just say a standard normal. This allows Stan to be much more optimized in computing both the likelihood and the gradient because it knows that both of these values, they're not going to be parameters, and it knows exactly what they're going to be to make it more efficient in computing the gradients. And finally here, rather than, as you can see in our likelihood, exponentiating our linear predictor and then passing it, we instead tell Stan that we're using a Poisson with a log link. This is important because when you work with exponentials, they can grow to be very, very large values or very, very small values incredibly quickly. When you're working with MCMC sampling that can jump around to value quite dramatically, especially at the start, it's important that it doesn't run out of numerical space. So by using a specialized distribution like this, Stan, when it's constructing both the gradients and the likelihood, it can be much more numerically safe when it's putting all of these terms together. All right, and then as quickly mentioned, we're also drawing predictions from our model. So given these linear predictors, based on our parameters that we've estimated, at each iteration of sampling, what does our model imply about the data? What data does this model suggest it should be seeing? And I'll tell you why we have that in just a second. All right, so now we have our model. So we've specified what data Stan should expect. So now let's put all that together. So in R, we have a list, which is just a container of differently typed objects. So we've constructed the number of individuals, the number of visits, number of predictors, an individual identifier for each person. Because remember, we have multiple assessments for each person. We need to know which assessments belong to the same one. And we've also got our predictors. So our treatment, our age, baseline, and the multiplication of baseline and treatment to be used for our interaction coefficient. And then finally, our outcome. All right, I breezed through that very quickly. Does anyone have any questions before we get to the running? Yes?
I'm sorry, it might be possible I missed it, but why did we not define the data type for the matrix or the integer data? There is no data type.
Yep. So matrices are like vectors and row vectors. They will always be continuous values. Yeah. No worries. Yes? Yes, yes. Yes, very good question. So the question was, are we assuming that each patient has the same number of visits? And yes, we are. Again, this is why it's very important when you're constructing your model to also identify what assumptions you're making when you're passing these in. So, great catch. Do we have anything else? All right. So if we run this block, we'll construct the data that we'll need. All right, and now we're ready to actually run the model. But of course, Stan is a compiled language, so we need to tell them to take our model and then compile it to an executable that can then run the sampling. So we just run this block, and our wrapper command stan R will take our model, translate it to C++, and then pass that C++ to the systems compiler to generate an executable. And then once that's ready, we can then pass our data and any other control parameters that we want to have it run. All right. Now, I will defend Stan a little here and say this is a bit slower in Colab than in real life. Okay, so now that we've compiled the model, it's been stored in this mod object. So mod contains a function called sample. By default, this will call our no U-turn sampler, and we just need to specify both the data and the settings that we want to use. So we're going to use our constructed data set, and we're also going to use 4 chains. Now, remember when we talked about MCMC, we talked about this idea that it has to find the probability density function. While that's fine when it's a simple shape like that, you can be working with very, very nasty posteriors sort of spread out in very different ways. So what we do is we start multiple Markov chains in random points throughout the parameter space, and you want them all to find the parameter space and fully explore it. So here we've specified that we want 4 chains, and we're going to start them at 4 different random points, and ideally they should all find the parameter space and all return the same quantification of our target distribution. And here we set the random seed that we use for identifying where those chains get dispersed. So while MTMC isn't very deterministic, as was mentioned, I think in the first day, you will often get very different results, you will get slightly different results run to run and between computers. By setting a seed which initializes where our chains start, we can have fairly roughly consistent results between all of our runs here today. You will also see differences based on different computers, because remember Stan is a compiled language, so it's going to take advantage of different CPU optimizations, and those can have very, very minor floating point differences in calculations. So you shouldn't expect numerically identical estimates between computers, but the results should be very, very consistent and inferences should not change. All right, so we've compiled our model and we're ready to call our sampling. So we run the command, wait for it to finish. Perfect. But we're not going to keep going just yet. So if we jump back to our workflow, remember, we've got a lot of steps. So our next step is this thing called a prior predictive check, which is the idea of if we have a model, before we've even seen any data, based on our priors and how we've constructed our model, what data are implied? So what we do is we simulate data from just the prior, and then we look at whether that data is realistic. So if we look at our Stan model, and we've got this RNG function, for a prior predictive check, we would remove or comment out this likelihood statement because we want no contribution of our observations to our likelihood. We just want to see what data does the prior imply. We're not going to do that for this because there is a better example. So what would happen if instead of a Poisson or a count, we had said we're going to use a Gaussian outcome. We're going to assume that our data are normally distributed. We ran the model, and these are the plots from the prior predictive check. So each line, so we've got 10 draws. We've got 10 estimates from our posterior. So at each iteration, we've generated the data according to our prior. So here we have 10 generations of data according to 10 iterations of our Markov chain. And we've got our density function across them. Can anyone identify why we would reject this model before we've seen any data? Yes?
Predicting negative number of seizures.
Points? Yes. So the issue here is that according to this model, people can have negative seizures. Medically impossible, I'd love to see it. They wouldn't. So immediately we would look at this and say, we don't even need to pass any data in. This is the wrong model for our situation. Because remember the principles we talked about earlier, fail early and fail fast. If your full model is going to take a long time to run when you have your data, you don't want to get this result at the end of 2 days of running. So if you run your check before the data and you see it's impossible, then you know to reject it and try something different. So what happens if our prior predictive check is failed and we move into this other step of the workflow? Well, we know it's not appropriate, so what do? Well, let's think about the data generating process or the likelihood that we've chosen. In this case, a Gaussian or a normal. Well, clearly that implies negative counts, so that's not appropriate. So it's about tying your statistical model back to the real life phenomenon that you're modelling, making sure that it's appropriate for what you're working with. And again, it's also very important to check your prior choices. Are we looking at impossible values, very wide values? Are we giving prior mass to negative seizures? All right, so at this point, we would have rejected the normal model and then moved on to using our Poisson, which we're very happy with. Now, the next steps would be to, now that we've run the model, validate our results and continue in our workflow. However, at this point in the workflow, it's time to have a break because coffee is ready. All right, everyone, so we'll start getting back into the next section and just wait for people to keep trickling in. All right, so if you remember where we left off just before the break, so we just run our model and we're ready to validate it. So we've done our prior predictive check, rejected our model, and then we've gone to our... Guys, we're starting now, if you could listen up, if that's all right. All right, so we've done our prior predictive check, we're happy with the Poisson, we've run the Poisson, and now we're ready to validate the result. So once we've run the model, how do we know that we can trust the results? How do we know that this computational numerical approximation is good for the model that we're using? So if you remember the two sources of bias that I pointed out earlier around MCMC, finding the probability mass and fully exploring the probability mass. We have two diagnostics that we work with for these sources of bias, and they fall under this umbrella of convergence. So if all of our chains have found the mass and fully explored it, theoretically, those chains should all be characterizing the same distribution. They should all be very consistent if they've converged. We assess this using what's called a trace plot, and we also assess this statistically using what's called an R-hat statistic. And I'll touch on effective sample size in just a second. So what do our trace plots look like? So really, this is just a graphical depiction of where our Markov chains have gone in the parameter space throughout our sampling. Ideally, we want to see that all of the chains have found the same place and they've explored it the same way. They've reached the same range of values. So you can see at the start of the plots, we have this very strange behavior of these points are very far away from the rest of the chains. This is that initial stage of our chains, of our Markov chains, finding that probability mass. It also contains the adaptation process of the NUTS sampler as it's finding the right parameters to be used throughout sampling. So rather than letting these biased estimates, letting this amount of bias influence our inferences, these just get discarded. The rule of thumb that most people use is they discard the first half of each chain as the warm-up or the burn-in procedure. It can slightly vary between different use cases. Really, the most important thing is making sure that you're not including any values from this point of finding the posterior mass, because that is where the most bias gets introduced. So normally we discard these points and you end up with a trace plot like this. So another way to visualize this, or to think about this trace plot, is to think of a density on the side here, like a normal distribution. So we see it bounces around the mean here and then ducks out to the tails. And what we want to see is that our sampler is efficiently and fully exploring the full range of values. And also we want to see that all of the chains are exploring the full range of values. Because what you might see is you'll have 3 chains in one spot, and then you might have another chain somewhere up here, just doing its own thing. And that can happen if you have a very geometrically tricky posterior, or if you've induced very strange priors. That can also happen if you have a multimodal posterior. So we see these a lot with Bayesian neural networks. We see these with clustering models like Gaussian mixture models. And it's very tricky for assessing convergence when you have these chains bouncing between different modes of the distribution and you're trying to statistically assess whether they're at the same point. So we have our trace plot to graphically assess convergence. But what if we want some kind of statistical measure and we're not just relying on researchers that say, we looked at trace plots and it was fine, please trust me. So if we have a look at what's called the R-hat statistic, this looks at the variance between chains compared to the variance within chains. And if that variance is very consistent, if it's identical, if all chains are exploring the same point and a single chain is converged within the same point, we would expect that R-hat to be 1, or very, very close to 1. Right. So those are our 2 key criteria for convergence: trace plots and an R-hat near 1. There are multiple cutoff values that have been proposed for this R-hat statistic. Some people use less than 1, some use smaller than 1.05, some use smaller than 1.01. The closer you can get to one, the better. The more rigorous and conservative you can be, the better. That's just something to be aware of. Now, actually, I also wanted to quickly cover this idea. So with these trace plots, you can see here that each point has bounced from each side of the distribution quite effectively. What you can also see is a Markov chain that's sort of gone down and then up and then down and then up, and it's taking a very long time to get from one side of the distribution to the other. And we call this poor mixing. The sampler isn't very efficiently exploring the full range of the posterior. There are two ways to deal with that. You can either reparameterize your model to represent the posterior in a more tractable way for it to explore. We'll touch on that a little bit later. You also see that people do what's called thinning, where they'll just discard iterations. So if you can roughly see that it's taking 1,000 iterations to get from one side to the other, well, we're just going to throw away that middle 1,000, and then we're just going to go up and down and up and down and up and down. But of course, that significantly increases your computational cost to fully explore the posterior. So that's not something that we generally want to do, but you might have to for some models. Yes? Yeah, so if your R hat is far away from 1, it's saying that either you have chains that have converged to a single point but in different places, or you might have chains that aren't converging at all. They haven't found the probability mass. They're not exploring it very efficiently. No, so that's why you always want to supplement with trace plots, because with R-hat statistics, if you run a chain for long enough, most times you can get down to a R-hat close to 1, even if the trace plot looks very bad. So you also can't tell what pathology is happening if you get a bad R-hat. Cool. Did we have any questions about convergence before I duck on? Oh, perfect. Now, the next big thing to check... Oh, sorry, yes? Very good question. So the question was, how do you decide how long to run the chains? There's two approaches. So with a lot of other samplers, things like JAGs and bugs, you can set a convergence target where they'll look at your R-hat and they will keep running until your chains hit the R-hat. We don't do that in Stan. Instead, ideally you just run and then you check afterwards to see if it converged. But in all of these cases as well, even after you've hit convergence, you still want to run the chains for longer, because you can have this idea of it might have falsely converged. It might look like they've fully explored the parameter space, but there could be a tricky part. Guys, if you're coming in, can you keep it down? Guys. Yeah. So you have this pathology called false convergence, where you might have a very easy to explore part of the posterior, but a very tricky part over here. So if you don't run the chain for long enough, it explores this easy part really, really well without touching this tricky part. But when you run it for longer, it starts wandering into there and your convergence gets terrible. So it's also a good check to run the chains for longer, even after you think you've converged. Any other questions around convergence? All right. So the next big thing to check is this idea of... Oh, sorry, yes?
Sometimes with these types of convergence plots, you'll look to see that your chain doesn't have any type of periodicity, right?
Mm-hmm.
And then what you'll do is maybe take like every 100 samples.
Yep.
Recently I was reading that that's not necessarily the best thing. It's not the most efficient way to sample. You can take every sample. You're not going to wait long enough to get rid of correlations or anything. You just use certain bounds on that. So what sort of, maybe later, do you have, in the workflow, are there some sort of recommendations for dealing with that type of problem?
Yeah, so the question was around this idea of thinning, removing iterations if the mixing is terrible or not very good. Generally, we advise against doing it. It can be, So as I said before, when the mixing is bad, so it's bouncing the other side very slowly, people will throw away parts of it, this thinning, and that will result in your convergence being good or better, these trace plots looking better. But at the same time, you're also throwing away information. Your sampler has found this point in the posterior and has identified it, and you're just getting rid of it. So in these cases, people will resort to this thinning because you have to run these chains for a very long time to get through all of the posterior if it's not traversing it very quickly. And when you think about computational limitations, you can only store so many values either in RAM or in disk. And if you have to run your model for 1 million iterations for it to properly explore, then it's not a good idea. So in that case, that is when they'll be thinning their samples so that they don't have to store the full 1 million iterations to get that proper exploration. So, yep. Perfect. Okay. Cool. All right, so the next big diagnostic to check is this idea of effective sample size. So if we remember our Monte Carlo estimator, I'll just duck back to the slide. Cool. So we have this idea of taking our expectation across all of these Markov chain samples. But a statistical assumption of this estimator is that these samples asymptotically will be independent. You have only so much information in each sample. So when we look at our effective sample size, I'll just get back to the right slide, the idea is that we want to identify, based on our posterior samples, we might have sampled for 2,000 iterations, how many of those are providing unique, useful information? How many equivalent independent samples would we need to get the same amount of information that we're getting from our posterior samples? So this becomes, what you're looking for is an effective sample size that is much, much smaller than your number of iterations in your sample. So let's say you ran for 4,000, so you ran 4 chains, each for 2,000 iterations, so you have 8,000 total. You discard the first half as warm-up, so you have 4 chains of 1,000 iterations that you're using for your inference. If you're looking at those 4 chains, those 4,000 total iterations, and your effective sample size comes out to like 100, it's saying that your exploration isn't very good. You don't have a lot of information from your samples. So you can't really trust any inferences you're making from these Monte Carlo estimators. So it's important to assess this effective sample size at the same time as you're making your inferences. And we actually separate this into 2 areas because we have the bulk of our distribution that can be quite easy to explore, and we have the tails where the probability mass can be quite thin and it can be quite difficult for our sampler to traverse. So we want to look at, in each of those, are we getting high effective sample sizes? Because if we just look at overall, you might have a very good effective sample size in the middle, and if you average out across the whole thing, it looks like you've done very well. But your effective sample size for your tails is terrible, and you're not getting good inferences there. So it's important to look at both. So what does that look like? All right, so if you remember just before the break, we were ready to run our model. We've compiled it. We hit run. Oh, no, I changed that and I shouldn't have. That won't be in yours. Yeah. So we've compiled our model, we've hit run. So we've got our 4 chains that are each starting from a random point in our parameter space. And we want to see whether those chains have converged to the same place. So we're going to look at our beta vector, which is our coefficient of regression weights. If we have a look at our trace plot using the MCMC trace function from the base plot package, we can see that all of our beta coefficients, age, treatment, baseline by treatment, they've converged to a consistent point. All of the chains are in a consistent place. We're not seeing different colors in different means. And the exploration is roughly pretty good. Ideally, for our final model, we might want to run this for a bit longer to see if that convergence still stays any better or gets any worse. So we've got our graphical check for convergence. Now we duck onto our statistical check, our R-hat, and then we also look at our effective... Sorry, yes? Yes, so by default, the first half are always removed from this plotting, yeah. So if we have a look at our summary statistics for our beta coefficients, and what we want to look at is our R-hat here, And we can see that our R hat is very close to 1. So we're seeing that all of our chains have converged to a consistent place, and the variation within those chains is very consistent across them as well. If we have a look at our effective sample sizes, and remembering that we've got 4,000 post-warm-up iterations, because we've got 4 chains for 2,000 iterations, and we've thrown away the first half, and we're seeing that our effective sample size, while not perfect, is still pretty good. Stan will throw a warning if your effective sample size gets down to less than 10% of your iterations. So generally, that's usually a very good cutoff. But again, with convergence, it's always a good idea to run your sampler for a little bit longer to see if that ratio of your effective sample size to your iteration changes appropriately, or if it gets better or worse. Yes?
How is the effective sample size influenced by other parameters?
Yeah, so it's based on the standard error of the actual Monte Carlo estimator. I've got that right? Yeah. So it's looking at the autocorrelation between your samples. And if your samples, sample to sample, the autocorrelation is very, very strong, well then your effective sample size is going to be weak because your samples are very far from independent. And it uses that through some other transformations to get the right ESS. In the Slack channel, I'll post a link to the reference for the ESS calculations and these bulk and tail as well, so you can see the different steps that go into it, if that helps.
But the other way around, can I somehow increase the effective sample size?
Yes, so you can, we'll touch on that a little bit later as well. Your effective sample size can be affected by, if you've got too many parameters for your data or your priors are very, very wide, there's way too much uncertainty, they can't find a good consistent value, then your effective sample size can go down as well. There isn't really one behaviour that causes the pathology, but it's a good sign that there is a pathology and you should investigate a bit more. Cool. Yes?
In case of a multimodal distribution, how common is it that it gets stuck in one of the modes and then it can never jump from one mode?
Yeah, very common. So the question was, with a multimodal distribution, how common is it that the sampler will get stuck in one mode and not go to the other? Very, very common. There was also a big issue for me during some of my modelling, because it happens a lot with Gaussian mixture models, where you're saying that there is a mixture of Gaussian distributions. There are 2 key issues that come up with that. So one is being able to identify the distinct distributions. So if they're very close together, your sampler might have difficulty identifying that it's in different distributions and it just looks as this very wide level of uncertainty. But on the other hand, if your modes are very far apart, you'll have one chain that finds one mode and fully explores it, and then you'll have another chain that finds a different one, fully explores it, and you have this, and then that will give you a very poor convergence because neither of those chains has found the other spots as the same spot as the other one. So things are very inconsistent.
Yeah, that was actually my follow-up question. So if that can happen, the 4 chains that you have on the top, like a plot, it could be that they're not looking similar because they're in different parts of the mode. So like, how do you know it hasn't converged, or is it like the 4 chains have converged to their own 4 modes?
Yes, so the question was how would you know whether they haven't converged or if they just converged to different points? So if that happens, you would see, I'll just make this bigger so it's a bit easier to see, actually. So when that happens, you would have a trace plot that looks like this, but you have 4 distinct chains, or 1 or 2, depending on which modes that they found. And within those chains, they're very consistent. So they found somewhere and they've converged, but they've converged to different places. That creates a lot of issues when we're looking at our posterior expectations because we've got very different chains in very different places. So there is a lot of work in how we reparameterize and force the chains to explore things in the same way, but it causes a lot of issues, and it's still a bit of an active area.
But can you not use the 4 chains to get like diversified samples in that case? Like, why do you want to force them?
So it comes to... Yes, the question was, why do you want to force the chains? So it's not so much about forcing them to the same place. The key issue is this idea of labeling. So you'll have, let's say, 3 different modes. One chain might find one mode and then the other mode and then the other mode, but the other one might find it in a different order. So for each chain, they've identified a different group as a different mode. So when your model is making inferences about the first mode, well, for one chain, that mode is over here, but for another chain, your first mode is over here. So it's about making sure that all chains have the same idea of what each mode are, as well as having properly explored them. If that makes sense.
That's what I did. Why do you do that? If I know it, this is a prior knowledge, and maybe like a pathological case, I know I have 4 modes, and I have 4 chains that are converged with each one. So is it legit for me to use each of those chains to get samples from 4 modes, knowing that there are 4 modes? Or is the assumption that each chain should have its own mode or broader?
Yeah, so it really depends on what you want to do with it. So if you're confident that all of the modes have been found and properly explored, and your inference isn't based on an expectation across the whole thing, then it should be okay. It's really about making sure that your analytic assumptions match up with what your model has estimated and what your model has found. Yeah. And again, there is no one right answer. It's very much a model depends kind of situation. Cool. Yes?
Effective sample size is not something you choose.
Yes. No, it's calculated. It assesses the quality of your sampling, basically. Cool. All right. Yes?
Since effective sample size is like a number, like how to interpret this number is like a fraction of something, like total number of samples, or how to use
Yeah. So the effective sample size tells you the number of independent samples you would need to have inference with the same level of confidence you're getting as with your current MTMC iterations. So if you get an effective sample size of 10, well, then that's saying that your inference is only as good as a Markov chain with 10 very, very good samples. So you want your effective sample size to be large to match the scale of your iterations. All right. Cool. All right, so at this point we've run our model and we've done some checking for the quality of our computation. Our convergence seems all right. Our effective sample size seems all right. So at this point it's time for us to evaluate our model. And what we want to do is to look at whether the model that we've now estimated in the context of our data is a good fit. So it's passed our prior predictive check, and now when we add our observations, does it still match what we're seeing? So a good approach here there's, I suppose, 6 different ones listed there, which I don't have time to go through, but a very effective one that we're looking at right now is called posterior predictive checking. So that's the RNG statement that you saw at the end of our model block, where it's just taking our parameters and then predicting what data our parameters imply at each iteration. And you end up with something like this. So we have the density of our observed data, and then you have the density of, I think this is 10 or 20 draws of predicted data based on our parameters at each value. And ideally what you want to see is that the model implied simulated data relatively closely follows or is a decent match for your observations. So if we want to do that in practice and we jump over to our notebook, we use this function from BasePlot where we want to overlay the density of our observations with the density of our predicted draws, which is this statement here where we're using a random number generator to generate draws from a Poisson based on these values of our linear predictor. Right. So how would we interpret this? So we can see that the density of our predicted draws is a bit higher at these smaller values than our observations. So this is saying that the model that we've currently chosen and that we've estimated seems to imply that we should be seeing a lot more smaller values than we currently are. It's a better fit for data with smaller number of counts. So what can we do to improve this? So at this stage, we've decided that we're going to reject our model. We think we can do better. So what else could we do instead? Well, let's have a look at the assumptions that our model is currently making. So we're using a Poisson. Now, this assumes that the mean and the variance of our outcome are the same. This might be a very strong assumption. The average number of seizures that people have might be very different from the individual differences in those seizures, the variance in those seizures. So what we can do is add a bit of flexibility to our model. So we include a random intercept or a random effect for each person. And this allows us to have a variance that is either greater or smaller than our mean. So what we're doing is we're adding to our model for each person a new random variable with a mean of 0 and a standard deviation of sigma. And again, like our model before, our standard deviation is constrained to be positive. And in this case, we're giving a half Cauchy prior. So this is a weakly informative prior, not assuming any particular value, but regularizing our level of uncertainty to something manageable. So if we have a look at how our new model looks now, so we've updated our model to now include, where has that gone? We've updated our model to now include this random intercept u, normally distributed with a half Cauchy prior. So in Stan, we're now adding another parameter for u, our random variable, and there is one for each person, so it's going to be a vector of parameters of length n, and we're also estimating the standard deviation of that, now difference between individuals. So we go to our model block and we add our priors. So we've got our half Cauchy because this is constrained to be positive. And we're also estimating our normally distributed individual differences, our mean vector. So we run through the same process of we ask R to compile this to an executable and we run it with our model. Wait for this to finish. So if I skip ahead a bit. So after we've run it with the model, and I'll show you the convergence diagnostics in just a second, we would then generate our posterior predictive check of our new model. And what do we see? We see that the densities of our implied values by our model, by our parameter values, are much more consistent with the data that we're seeing. Our model, our idea of how the treatment is affecting changes in seizures is a much better idea for our observations of changes in seizures over time. So when we want to make predictions or we want to make inferences, we now have a lot more confidence because our data is a much better match for our model, or our model is a much better match for our data. So if we have a look at our completed chains, so we're going to run through the same process of we have a look at our trace plots, and we're going to look at our summary statistics. So we can see that after we've run the chains, overall the convergence is decent. You can see some examples of not great mixing. And you can also see our effective sample size has dropped a bit. So where before we were up in the 1,000 or 2,000s, we're now down in 700 to 800s. So what this is saying is that we've got a model that's a bit more complex and our sampler isn't exploring it efficiently in the number of iterations that we've given it. And we'll show you a fix for that in just a moment. All right, so sorry, yes?
Is this method of working sensitive to overfitting to your training data? Did you sort of keep re-specifying your model until you have
It comes down to what you're trying to achieve. So if the goal is to find something that is more generalizable to new observations, then part of your workflow is that cross-validation and leave one out validation. But if your goal is to make inferences, then you want something that is best able to describe what you're seeing. But it's always going to be a balance between the two. Cool. All right. Yes?
We find this mu by a normal distribution. Could it be that the lambda is then negative?
Yep. So the question is, we defined mu as a normal. And we didn't place any restrictions on mu, so couldn't it be negative? But what we've done is our random intercept has gone into our, it's on the log scale, and it's been exponentiated. Cool. Right. Do we have any? Yes? What do you mean by extend to a multi-dimensional case? Sorry, I'm not sure. Yes. So the question was, like, can we extend this visualization to multi-dimensional cases? I might not be answering exactly the question that you're asking, but if it's a quantity that's been estimated, you're just looking at whether that estimated quantity is consistent in all of its iterations. That might not be the perfect answer to your question, but I can pop some resources into the Slack channel around how the convergence is used with things like spatial models and things a bit more complex like that. Yes?
Maybe a question. Assume we have a multi-dimensional output and these are correlated with each other. How would we visualize whether the correlations are replicated correctly?
Excellent question. So the question is, if our outcomes are correlated, how do we visualize that there has been captured by our distribution, or our model? That's exactly my research and my work at the moment, so you've come to the right place. It's a bit of an ongoing sort of question. So if you have only a small number of outcomes, you can specifically look at the distribution of those correlations and how it matches with your observed correlation. But if you have many, so if you're looking at like hundreds of outcomes, 100 by 100 matrix is going to be very hard to sort of graphically assess. And at that point, you have to start collapsing down to things like eigenvalues or some sort of reduction technique, and then look at how those are reproduced by your model. But yeah, there isn't one simple answer, and it's still very much an active area of research. Cool. Do you have any more questions? All right. Cool. All right, so we now have a model that we're provisionally happy to accept. We might want to run it for more iterations just to make sure that our computation stays stable, but overall we're roughly happy. So what do? Well, we can just stop here, but we don't think that we have exactly the best model or the best choice for ourselves. So let's say, for example, this treatment trial is being run by a pharmaceutical company, and they're planning on scaling it up to something that has 300, 500, 1,000 people being assessed. Or it might be a model that's going to be put into some sort of production, and it's going to have to be run 1,000 times a day. At the moment, this model is fairly computationally expensive, and it's not going to scale well, because we're estimating an additional parameter for every person that's included in the trial. So as we scale up, that's going to get slower and slower and slower. So how can we work around this? So what if we used a different distribution for this random UI? So, for example, in this case, we're going to start with a gamma distribution. And we're going to parameterize the gamma using a single parameter for both the shape and, in this case, the rate. And I'll give you the intuition for why we're doing that in just a second. So we're going to have a new model where we replace our normally distributed U with a gamma distributed theta, characterized by one parameter. So if we have a look at our model, we have our new model that we want to estimate. Now in Stan, what we've done is we've changed our distribution from U to a gamma with the same parameters, and we're now estimating a shape and a rate parameter instead of a standard deviation. Now, you notice also that here I'm adding the log of U. This is because we're multiplying lambda here. So where above with our normal, we were already modeling it on the log scale, and it was fine. In this case, we're modeling gamma on the natural scale. So we're going to take the logarithm of it so then we add it into our linear predictor in the same way. So if I run and fit that, what we end up with is very, very similar fit to our data. This approach of estimating one parameter per person still seems to be effective or appropriate for our model. But then the question is, well, we're still estimating the same number of parameters. What was the point? So this is because there's a very useful trick that you can use in a lot of situations called marginalization, where you're essentially summing out a parameter from your likelihood by still characterizing the same contribution of that parameter to your likelihood without directly estimating it. Incredibly vague. I'll give you an example in a second. So some people among you that are familiar with count modeling might have recognized that when you have a Poisson with a gamma distributed rate parameter, you can marginalize that out to a negative binomial. So what we have is our Poisson likelihood with our gamma prior. We can get exactly the same likelihood contribution without directly estimating that theta. And we just use simply our observed data, well, and the other parameter lambda and phi. So because you're all very rigorous data scientists and Bayesians, I wouldn't expect you to trust me at my word on something this important. So what we're going to do is we're going to verify this. So here I've specified a linear predictor for lambda, a particular count for y, and our dispersion parameter phi. And what we're going to do is we're going to integrate across our likelihood. So we have our Poisson with our outcome and our same lambda times theta. And we have our prior for theta, which is a gamma, with equal shape and rate. And what we're going to do is we're going to integrate across all possible values of theta to get the likelihood contribution. And then we're going to verify that it's the same when we use a negative binomial. So our first result is going to be the integration. And the second result is going to be our negative binomial density. So when we run that, what we see is, that's a little tiny, what we see is that our numerical integration gives us the same value for the density as our negative binomial. So what that means is we can represent our posterior using n less parameters. We can save that much computation and still have the same model. So if we have a look at Stan, so we're still using a very similar construction, but now we're no longer estimating that vector for u. We've got n less parameters. It's not being added to the lambda. And we now have a negative binomial distribution. In this case, when in Stan, the negative binomial 2 is a negative binomial parameterized by its mean and its dispersion, rather than the R or a P parameter, which you've seen in some constructions. And we've now changed our prediction statement to also use this new negative binomial distribution. So if we run this model, what we see is, so we have our new likelihood, negative binomial, just with that n parameters marginalized out. And if we run that, we see pretty much the same fit to the data. Very, very good posterior predictive check. And if we have a look at our runtime, we've dropped it dramatically while still having consistent inferences and consistent estimates. But of course, you guys are all very ambitious. You want to climb the ranks of this pharmaceutical company. So you say, we can do a little bit better. And this is the point where you start thinking about what your model is actually doing, or what Stan is actually doing with your model. So remember, we're constructing our linear predictor as the multiplication of our data with some parameters, beta, and adding alpha. But because Hamiltonian Monte Carlo needs to propagate gradients through all functions that contribute to the likelihood, that means for each element of this linear predictor, each n elements, we have to calculate the gradients for each of those. In Stan, what we can do is use a specialized GLM distribution where we pass each of these terms individually, and Stan knows that we don't really care about gradients with respect to x because it's data. We're only going to calculate gradients with respect to alpha and beta. We're not going to go through that process of propagating the gradients all the way through. So if we have a look at our notebook, we can see a GLM distribution where instead of constructing our likelihood like this, alpha plus x times beta, we're passing the terms individually. So now Stan can detect which items are data, which items are parameters, and be much more efficient in how it calculates gradients. So if we run this model, you'll end up with a posterior predictive check that is pretty much identical, because the likelihood, remember, is identical. It's exactly the same likelihood. It's just reducing the number of unnecessary gradient computations. And we can see that using this GLM distribution has dropped our runtime in half from the regular negative binomial, and it's now taking about 1/10 of the time of our normal random effect. And it also means it's going to scale even better with new data, because we're now no longer doing n gradient computations to construct this linear predictor. So it's very important when we're looking at these things to consider both your likelihood and your statistical construction, as well as computational aspects of the program that you're using. All right. So at this point, we've now made our way to the very end of the workflow. So we're happy with our Poisson normal random effect and our negative binomial with a GLM. Now, most people are going to jump straight to the negative binomial, but what if you want to make sure that you're really using the right model? We want to make some sort of comparison and check here. So a really good one is to look at the inferences and the quality of those inferences that are coming from your model. So if we look at our posterior for the treatment effect, we can see that our mean, I've got to stop clicking on things. We can see that our mean is negative 0.27. So that's on the log scale, it'll be exponentiated. And we can see that our 95% credibility intervals range from negative 0.5 to just above 0. And we have our ESS there. But if we look at the same posterior, but from our negative binomial GLM, we can see that even though the mean isn't quite as negative, it isn't estimating as big of an effect, our estimates are much more precise, much narrower. We no longer go across such a wide range of estimates, and also the quality of our estimates are so much better. We're now looking at ESS of over 2,000 rather than 700. So we've ended up with a model that's both faster to estimate, and the estimates that we're getting out of it are of a higher quality. We have more confidence in the inferences that we're making. All right, so that brings us to the very end of this workflow. So hopefully I've covered some of the key parts of building these models, checking each stage of these models, and really making sure that if you're going to fail, you're going to fail early and you're going to fail fast. Statistically, not in your career. So hopefully this has presented a good introduction to a structured workflow. If you have more questions, you can have a look at the Bayesian workflow paper by Andrew Gelman, which I'll post in the Slack, and also Elizaveta Semenova's presentation from last year, which also touched on these topics from a slightly different perspective, which might be more helpful if some of this didn't quite land for you. But thank you very much for having me.